All right, welcome back to the deep dive. Today we're diving into a paper all about decision trees.
Decision trees.
Yeah, but not the usual kind. These are neuro-symbolic decision trees.
Okay, so we're bringing in neural networks and symbolic AI. I see where this is going.
Exactly. The paper is titled Neuro-Symbolic Decision Trees. Pretty straightforward, and they introduce a new learning algorithm called NDT.
Interesting. So what's the big deal about these neuro-symbolic decision trees? Why should our listeners care?
Well, the authors tackle a pretty big challenge in AI. You know how in neuro-symbolic AI, we often have to predefine the structure of the logic, kind of like setting the stage before the actors even come on.
Right, and then the neural networks learn the parameters, the specific values within that structure, like figuring out their lines and actions.
Exactly. But what if we don't even know the best structure to start with? What if the play is still being written?
That's where this research comes in. These NDTs, these neuro-symbolic decision trees, can learn both the structure and the parameters at the same time. They're building the stage and figuring out the play as they go.
Pretty cool, right? And this has some huge implications. Firstly, these NDTs can learn from all sorts of data, not just symbolic data like facts and rules, but also sub-symbolic data, think images, sensor readings, stuff like that.
So they're not limited to just working with those crisp, logical statements. They can handle the messy, real-world data too.
Exactly. And secondly, you can use any background knowledge you have about the domain. If you know some rules or facts that might be helpful, you can feed that into the learning process.
Makes sense. If you already have some pieces of the puzzle, why not use them?
Exactly. And the coolest part, the system can learn the structure of the symbolic model from scratch, which is a big departure from how a lot of neurosymbolic AI is done now.
So they're not just filling in the blanks, they're figuring out the shape of the puzzle itself. That's impressive.
All right, let's walk through the paper step by step. First, they lay out the basics of neurosymbolic AI, which is this idea of combining neural networks, those pattern recognition machines, with symbolic AI, the world of logic and rules.
A powerful combination, if you can get it right.
For sure. They explain how a lot of current neurosymbolic systems use probabilistic logic formulas. Neural networks predict probabilities within those formulas, but, as we said, the structure of those formulas is usually predefined.
So that's the bottleneck they're trying to break through.
Yep. Now they introduce their solution, Neuro-Symbolic Decision Trees, or NDTs. Imagine a decision tree, but at each decision point, at each node, instead of a simple rule, you have a neural network making the call.
I see. So instead of asking, is it raining? The tree could ask, does this image, as analyzed by a neural network, show a high probability of rain clouds?
Exactly. It's like giving the decision tree a set of superpowered eyes.
To learn these NDTs, they've come up with a new algorithm called NewID3. This algorithm, inspired by the classic ID3 algorithm for regular decision trees, builds the NDT step by step from the top down, refining it as it goes.
So it starts with the whole data set at the top, then makes splits, creates branches based on the best tests at each node. And these tests can involve neural networks making decisions based on complex data.
Got it. So they're growing this tree of logic, but with neural networks embedded in the decision making. That's a neat visual.
And a key advantage here is that NDTs can handle both symbolic and sub-symbolic data, integrate background knowledge, and, as we've said, learn the symbolic structure from scratch. They also mention that while this work focuses on propositional logic, the simpler kind, they think it could be extended to first-order logic, which can handle more complex relationships.
That's a promising avenue for future research. But before we get too ahead of ourselves, let's make sure everyone's on the same page about the logic part. What are the essentials of propositional logic that underpin all of this?
So they remind us about propositional logic programming, starting with the idea of atoms. These are the basic building blocks, like the cat is on the mat, simple statements that can be true or false.
Right, the most basic facts we're dealing with.
Then there are literals, which are atoms or the negations, so either the cat is on the mat or the cat is not on the mat.
So we're covering all the possibilities.
Then we have rules, which are like if-then statements. If the cat is hungry and the food bowl is full, then the cat will eat.
The classic logic puzzle setup.
A logic program is a collection of these rules and some basic facts, and then logical consequence is figuring out what must be true based on that program. So if we know the cat is hungry and the food bowl is full, we can conclude that the cat will eat.
Classic deduction.
Okay, now they move on to Boolean decision trees, or BDTs. These are the classic decision trees, where each node is a yes-no question based on a proposition. For example, is the cat hungry? The branches represent the answers, and the leaves at the bottom tell you the final classification.
So it's like a flowchart for making decisions based on a series of true-false questions.
They use the example of a burglary alarm going off, whether there's a burglary and whether there's an earthquake, to illustrate how a BDT can be represented as a set of logical rules. So each path in the tree represents a different chain of reasoning, leading to a specific conclusion.
Makes sense.
Now we get to probabilistic Boolean decision trees, which are more realistic because they deal with uncertainty. Instead of saying the cat is hungry with absolute certainty, we say there's a 70% chance the cat is hungry. It's a probabilistic fact.
So we're introducing probabilities into the mix.
Each branch now has a probability associated with it, and an example can end up at multiple leaves with different probabilities. They talk about how to calculate these probabilities using something called weighted model counting, which essentially weighs the likelihood of different possible scenarios.
So instead of just one definite path, we have a distribution of possible paths, each with its own weight.
Right. And at the leaves, instead of a definite class label, we have a probability distribution over classes, like 60% chance it's a tabby cat, 40% chance it's a Siamese cat.
So even the final classification becomes probabilistic, reflecting the uncertainty throughout the decision process.
Okay, so now that we have the basics of decision trees and probabilistic logic, how do we bring in the neural networks?
That's where things get really interesting. They introduce probabilistic neural decision trees, where the probabilities of facts at the nodes are predicted by a neural network. So instead of just saying there's a 70% chance the cat is hungry, a neural network might look at an image of the cat's food bowl and say there's a 90% chance the bowl is empty, therefore a high probability the cat is hungry.
That's cool. The neural network is basically acting as a smart sensor, providing more nuanced information to the decision tree.
Right, and then they introduce neuro-symbolic background knowledge. Imagine you have a rule like, if the cat ears are flattened, then it's likely scared. That ears are flattened part could be a neural predicate, something learned by a neural network from images of cat ears.
So we're combining the perceptual power of neural networks with the symbolic reasoning of logic.
Exactly. Now, they formally define NDTs as binary trees, where those tests at the nodes can be anything. A regular fact, a probabilistic fact, a neural fact predicted by a network, or even a whole neural rule, like the ears example. The leaves of the tree hold probability distributions over the classes.
So it's a very flexible framework that can accommodate a wide range of information.
And crucially, they show how you can represent and reason with these NDTs using probabilistic logic programming systems like Deep Problog.
So we have a way to both learn these structures from data and use them for making predictions in a principled way.
Okay, now the big question, how do you actually learn these NDTs from data?
That's where the new ID3 algorithm comes in. This is a top-down iterative algorithm that starts with a single node representing all the data and then keeps refining the tree, adding tests at the leaves until it reaches a stopping condition.
So it's growing the tree step by step, choosing the best tests to split the data at each point.
Right, and those tests can involve neural networks, which need to be trained. Now, you can't just use regular cross-entropy logs to train these networks because examples only reach certain parts of the tree with some probability.
Because of those probabilistic branches, right?
Yeah, and also you might end up with some class imbalance in the deeper nodes. So they use a weighted cross-entropy loss that takes these factors into account, ensuring the networks are trained properly.
Smart. They're adapting the loss function to fit the unique characteristics of the NDT structure.
Oh.
So how does the algorithm decide which test is the best to use for a split?
They use a modified version of the classic information gain metric called, cleverly, information gain with probabilities. This measures how much a test improves our ability to predict the class label, but it takes into account the probabilities involved in the splits.
So instead of counting examples, they're working with probabilities.
Exactly. The test with the highest information gain, the one that tells us the most about the classes, is chosen as the best split. Now, how does this all stack up against existing work?
They do a thorough review, comparing NDTs with other decision tree methods, like soft decision trees, which also use neural networks for probabilistic splits, and other neurosymbolic learning approaches. The key takeaway is that NDTs offer a unique combination of features: learning the tree structure, handling both symbolic and sub-symbolic data, incorporating background knowledge, and doing all this within a solid probabilistic logic framework.
It's like combining the best features of different approaches.
Now, what about the experiments? Did they actually put these NDTs to the test?
They did. They tested on the UCI datasets, those classic machine learning benchmarks, but also on modified versions where they swapped out the symbolic features for images, creating the USymnist datasets. They also used the Elusis card game dataset, which is all about learning hidden rules.
So a good mix of symbolic, sub-symbolic, and rule learning tasks.
They compared NDTs with standard multi-layer perceptrons, MLPs. On those UCI datasets, NDTs performed on par or better than MLPs, especially when dealing with the image data, where MLPs often struggled.
That's a good sign for NDTs.
Yeah, and NDTs were much more consistent in their performance across different types of data, while MLPs showed a significant drop in accuracy when switching from symbolic to sub-symbolic data.
Adaptability seems to be one of the strengths of NDTs.
And on the Elusis dataset, NDTs also outperformed a specifically designed neural network architecture, showing their strength in rule learning tasks.
Impressive.
Now, they highlighted incorporating background knowledge as a big advantage, so they tested that too. In the Elusis experiments, they gave NUID 3 different sets of potential tests, some containing optimal rules, some containing a mix of good and bad rules, and even some with no rules at all.
So they were testing how well NDTs could use prior knowledge and how robust they were to bad knowledge.
And the results were clear. Providing good background knowledge really helped. But what was even cooler was that NUID 3 seemed to be able to figure out which rules were useful and which weren't. It wasn't blindly following bad rules.
So it had a sense of what was actually informative. That's important.
They also did a cool experiment where they trained neural tests to recognize suit order and rank order in cards, and then used those pre-trained tests to learn a more complex rule that combined those concepts.
So they were testing the reusability of learned components.
Exactly, and reusing those tests significantly sped up the learning of the new rule.
That's exciting. It hints at the possibility of building more modular, adaptable systems.
All right, so to wrap it up, this paper introduces Neuro-Symbolic Decision Trees, a very promising way to combine the best of neural and symbolic AI. They can handle diverse data, learn structure and parameters, use background knowledge, and they've shown strong performance in experiments.
Definitely an approach worth keeping an eye on. Now, for our Novel Notions segment where we go beyond the paper and explore potential future directions, what are some exciting avenues for research based on this work?
Building on their work with reusing neural tests, I think one really interesting direction would be to look at continuous learning with NDTs. Imagine a system that doesn't just reuse components for a single task, but keeps learning and evolving its neurosymbolic knowledge over time across many different data sets and problems.
Like an NDT that keeps growing and refining its understanding of the world. How would that work?
Think about a robot learning to navigate and manipulate objects. Maybe it starts with simple shape detectors. Then, as it encounters new objects and tasks, it could reuse those shape detectors, but also learn new neural tests for textures, colors, materials. It could even learn higher-level concepts based on combinations of these features.
That's a fascinating idea. It's like building a hierarchical knowledge base, constantly expanding and adapting.
Right, and this could be a way to address catastrophic forgetting, where learning new things wipes out old knowledge. It's a big problem in continuous learning with neural networks, but because the knowledge in an NDT is structured logically, it might be more robust to these changes.
But wouldn't it get messy over time? How would the system know when and how to reuse or adapt existing components?
That's the big challenge. We'd need smart algorithms to manage this process, perhaps even using meta-learning to optimize the reuse and adaptation strategies themselves. But if we can crack this, it could lead to more adaptable and robust AI systems that can learn continuously throughout their lifetime.
So moving towards more general human-like learning.
Exciting.
What else caught your eye in terms of future research?
Another big one is using NDTs for explainable AI, especially in areas like medical imaging. Right now, deep learning models are great at diagnosing things from scans, but they're black boxes. We don't really know why they make the decisions they do.
Which is a huge problem for trust, especially in healthcare. You don't want to just blindly trust a machine with life or death decisions.
Exactly. But with NDTs, because of their logical structure, you can trace the reasoning behind a diagnosis. Each path in the tree represents a set of conditions, a logical rule that led to that outcome.
So instead of a mysterious prediction, you get an interpretable explanation.
Right. And you could even incorporate existing medical knowledge, like symptoms and risk factors, into the tree as neurosymbolic rules, further improving both the accuracy and the interpretability. Imagine a doctor being able to see Not just the diagnosis, but also a clear, understandable set of reasons why the AI reached that conclusion.
That would be a game changer for the adoption of AI in medicine.
Absolutely. But of course, the challenge there is dealing with the complexity of medical images while still maintaining a level of interpretability that's useful for doctors.
A lot of work ahead, but with a huge potential payoff.
All right, so to sum it all up, neuro-symbolic decision trees are a really promising direction for the future of AI, combining the power of neural networks with the transparency of symbolic reasoning.
And they open up exciting new possibilities for continuous learning, explainability, and more.
For our listeners who want to dive deeper into the technical details, you can find the link to the paper in the show notes.
And be sure to join us next time on The Deep Dive as we continue to explore the frontiers of machine learning research.